name is Johnny O'Brien. This is my student project for Engineering Tech 195 Advanced Surfacing. My project was on the BE-183 airfoil and how I plan to use it in a motorsport application. Alright, so just a quick overview of the BE-183 airfoil. It was initially designed by Boeing. It was used in general aviation. It's known for its moderate thickness. It has an 18% chord length, which gives it a good lift to drag ratio, and it really stabilizes the stall characteristics. It gives the best of both worlds in the terms that it gives you good drag, but not enough to where if your airflow is disrupted, you're going to be out of the water. Some of the key aerodynamic properties of it are the high lift, moderate drag, and the predictable stall. It makes it just a well-rounded airfoil, tried and true. Yeah, nothing too crazy about it. The objective of this presentation is to explore how the BE-183 airfoil could potentially be applied to motorsports, especially in vehicles requiring high aerodynamic performance, like racing cars, motorcycles, and other motorsport applications. First of all, sorry for the picture quality on the bottom right. I was having a couple issues importing the pictures of the prototypes in, but they're kind of there. So, this is the basics for airfoils. You may be asking yourself, what even is an airfoil? The cut and dry definition of an airfoil is a surface designed to generate lift when air flows over it. So basically, it's a shape, and the camber determines the airfoil's aerodynamic properties. So you can see up in the top right, that's just like the basic characteristics defining properties of what changes between different airfoils. So you'll have all of these different terms throughout them. Every airfoil has a leading edge, upper camber, the mean camber and or medium camber, the trailing edge, the chord. It has all that. It's just dependent on what those values are. Really changes the properties of what that airfoil does, and therefore changes the applications of it. So some of the basic aerodynamic terms that I'm going to be using throughout this are lift, which is the upward force generated perpendicular to the airflow. Drag, the resistance that opposes the motion through the air. Stall, a condition where the airflow detaches from the airfoil, leading to loss of lift. The BE-183 design has an 18% thickness and the chord length. So that means that the thickness of the overall airfoil is 18% of the overall length of the chord. So you can see in the top, the chord runs from the leading edge to the trailing edge. So that means the distance between the lower camber and the upper camber will be 18% of that total distance. This aggressive ratio gives it a really good high lift to drag ratio, although it's not too aggressive of a ratio. So if that upper camber was more aggressive, so say 25% of the overall chord length, it's going to be hard for the air to stay attached to such a curved surface. So when it gets to that top point on that upper camber surface, it detaches. And when that air detaches, that's called stall. And then when you get to stall, your airfoil is doing nothing. It's not giving you anything, it's just hurting. So the whole point with wings and with the aero is pretty much get as close to that stall point as you can. So get as much camber, get as much of that wing as you can without causing the stall, without having that air detach. So later you'll see a lot of people, they use what's called an air rake. It's basically like a little L bracket that goes at the lead or the trailing edge of a wing. And the point of that is it really just helps kick that wing down, helps keep the air attached to that surface, so then you can have a higher degree of camber on it. Excuse me. Alrighty. So, some of the reasons why I went with the 183 airfoil was the thickness. It offers great strength. You can use it for heavier loads. I'm planning on having this wing take a couple 100 pounds of downforce pretty regularly, so I wanted something that was going to be able to at least support my body weight minimum. Like I've said before, has a moderate camber. It's really balanced lift to drag. This is my first kind of dive into aerosport or aerodynamics in motorsports, so I really wanted to go with something that's tried and true. I didn't want to be the first person to do it. I don't want to reinvent the wheel either, but I do want to get the knowledge that you get to go with that, I guess, timeline. So here we go. Some of the individual parts for this assembly were the wing surface, which you see up on the top there. I just took the surface directly from a 183 airfoil that I bought at home, traced it out, extruded the surface, and then you can see on that back edge up here, I also put the L rake on there. That's just a 1/2 inch L that I extruded along as well. That just helps the air stay attached to that bottom edge. And then on the bottom left, you have the wing uprights. I initially designed these to just be cut out of sheet metal, just flat, I believe 1/4 inch, 70-75 aluminum. But now that I've gotten deeper into the design and I've added chamfers and I've done a couple of things with it that I just think add to the overall aesthetic design of it, because I really want the aesthetics to match the performance. I think I might get them machined out. It'll be more expensive, but it's baller. So, you know, you give some, you take some. And then on the bottom right, these are the end plates. The company that I got the BE-183 airfoil through, they had already designed these end plates. I'm just kind of going with them for now. I'm not super happy with them. They're pretty small. So what I think I'll end up doing is I'll end up just using them to get these mounting points so that I know where to mount it to the wing. And then I'll end up making an extended end plate that kind of goes and has a joggle up here and comes further up, and then it'll have a mounting point for a second element, which is basically a mini wing up here that you can then have a linear actuator mounted to, so you can adjust the rake angle on that second element. It's called a DRS system. It's the next step, but I didn't get to that on this project. It's a little advanced. I wanted to make a wing before I tried to make an advanced wing, I guess. So these are the brackets. Both of these brackets were designed off of scan data. I scanned the top of the wing, took that surface to get this bottom surface, and then I scanned the back of my car and took this surface to get this thick surface for the bottom plate. So this is like, has contours in the X, Y, has ER rotation, and then one other rotation. That, don't quote me on that, or that could be wrong. So yeah, these are those two mounts. These are both going to be machined out of 70-75. I'll probably ship that out just because I do not have access to a 5-axis. No pun intended. So this one's kind of hard to see, but this is the CFD, the computational fluid design on this. So it pretty much just shows that the fluid will flow. They use fluid because it works the same as air, you know, airflow, fluid flow, hydrodynamic, aerodynamic. So yeah, they pretty much just went through, and that's why this is the wing I went with. It's tried and true. It could optimize the high lift capacity while maximizing grip. It has the gradual stall characteristics, like I've already said, and you know, it produces pretty low drag for the lift. So it could be kind of suited for either or. I could make a more aggressive attack angle if I want higher drag. I could do a less aggressive angle if I want less drag, and then I could do a DRS, a second element, to increase the drag when needed with braking, but time will tell. So a little bit more. This is a course that I've been taking. This is some of the computational fluid design to show where the stresses are. So these are the high air pressure zones are up top here, and then the low pressure is on the bottom here. So this is, you always want these bottom surfaces to have as low of pressure as possible, so that when you have the high pressure on the top, it pushes down and there's not much force pushing back up on it. This in turn creates what we know as downforce. So yeah, CFD, super interesting stuff in my opinion. If you can learn how to do CFD, you can bypass so many stages of research and design. You can save a lot of money in a lot of different prototypes. So it's a super useful function that not a lot of people use. 3DX has some great CFD and FEA applications. I should probably do like a video on those in the future, but it's pretty advanced stuff. It's really cool. Okay, so these are the conclusions. The BE-183 offers moderate lift, low drag, stable aerodynamic characteristics. It's a promising candidate for motorsport applications. It's, for lack of better terms, a blank slate. It could be used for race car wings, motorcycle fairings, and aerodynamic testing. With those race car wings, it could be used for a front and a rear wing. You could also do a mid wing with it, but the mid wings are a little confusing just because it's hard to judge what type of air you'll have there, as in if it'll be clean air or if it'll be messy air, meaning disrupted by the flow of your car moving through the air versus it being the first thing of your car touching the air. This kind of just restates that first point. So yeah, my brother and I plan on optimizing the shape, and then we're going to make it out of composite. So carbon fiber is the goal, and we will inlay all of the bracketry and stuff. When we do that, though, I would like to do that with the DRS system. With that package, it would be a wing that could probably sell for 5,000 to 6,000. I would hope, but time will tell. There, we have to make it professional. So yeah, the next steps are pretty much, I'm going to do another prototype. I might make these a little bit bigger. I don't know if I like the scale or not. And then I'm going to print out the passenger side after I get this one right. I need to get a bigger printer so I can print these in one piece, as I've been having a couple of issues just attaching the uprights together. But yeah, once the design's been finalized, I'll finish making all the proper constraints in 3DX, and then I will do the FEA. I'm planning on just mounting down, locking all of these mounting points, and making it so this bottom bracket, which attaches to the car, is not able to move. And then I will apply loads equally across this upper deck until either the brackets, the mounting hardware, or the upright gives out. So we'll see how that goes, but I'm excited for that part. And yeah, planning on attaching this bracket to the wing, either through rivets or through just aerospace adhesive. Gonna have to do more research there. And then the bracket that gets attached to the car side will be bolted through. It sits pretty much right on top of the latch for the hatchback. So I'm hoping that since the forces will be transferred right through there, it'll be able to go to the frame more effectively, and we won't have any issues there. But time will tell once again. But yeah, that's all I got. Thanks for watching, and take it easy.